Imagine an invisible absolute force sweeping across empty space. An external electric field dictates the movement of any free charge it touches, instantly dragging positive and negative particles in opposite directions. Look at how a standard metal conductor reacts to this force. Because metals are full of highly mobile free electrons, those negative charges immediately rush to the surface to get as close to the incoming field as possible. By separating its charges, the metal builds its own internal electric field, pointing exactly opposite to the external one. Those two forces perfectly cancel each other out. Inside a static metallic conductor, the net electrostatic field drops exactly to zero. Now watch what happens when we swap that metal out for an insulator, what physicists call a dielectric. In this block, electrons are firmly locked to their parent atoms. They cannot freely flow across the material to build a defensive shield. Yet the dielectric still pushes back. Without a single free-flowing charge, it somehow generates its own opposing force. It isn't strong enough to perfectly cancel the external field, but it visibly reduces the total field strength inside the block. If the charges are entirely locked in place and unable to reach the surface, how is this rigid material fighting the field? To find the answer, we have to scale down and look directly at the atomic structure of the material. Take a nonpolar molecule, like oxygen. Left entirely to its own devices, the centers of its positive and negative charges overlap perfectly. It is highly symmetrical, balanced, and perfectly neutral. That balance holds until an external electric field strikes. The field physically pulls the atom's structure. The positive nucleus is forced in the direction of the field, while the negative electron cloud drags backward. The perfect sphere stretches into a strained, tense oval. This forced separation is called an induced dipole moment. It is the absolute physical limit a molecule can stretch, creating a tiny temporary separation of charge before its own internal chemical bonds pull it back together. Without a single electron breaking free from its orbit, the field's physical stress has forced the material to create microscopic, localized pockets of charge. Other dielectrics take a slightly different path. Consider a polar molecule, like water. By its very nature, it already possesses a permanently separated positive and negative end. Because of their separated charges, you might expect water to project a strong, unified electric field. In reality, thermal energy keeps these molecules tumbling in constant random motion. Their individual arrows point in every direction, completely canceling each other out, until the external field penetrates the chaos. The incoming field acts as an invisible, unifying grip. It overpowers the random thermal tumbling, violently snapping the chaotic molecules into strict geometric alignment. Every positive end is forced to face the field. Whether the field stretches perfectly round molecules into ovals or wrangles chaotic polar molecules into uniform rows, the mechanical outcome is identical. The field has created a disciplined, microscopic grid of dipoles, all pointing back against the external force. Zooming out, the dielectric is packed solid with uniform rows of dipoles. Inside, they stack head to tail. Every positive charge neutralizes a neighboring negative one, leaving the interior neutral. But at the extreme edges, this chain breaks, leaving entirely exposed layers of unneutralized surface charges. This creates what physicists call an induced surface charge. By simply stretching and aligning its locked molecules in place, the dielectric successfully mimics the surface defense mechanism of a metal connector. We quantify this collective molecular alignment as the net dipole moment per unit volume. The formal term for it is polarization. The intensity of this polarization varies by material. It depends heavily on a metric known as electric susceptibility, a constant that measures exactly how easily a specific material's internal structure yields and aligns to an incoming field, which finally resolves our opening mystery. How does a material with locked-down electrons manage to push back against a powerful external field? It all comes down to those unneutralized boundary layers. The newly exposed negative and positive surface charges project their own internal electric field. This new field points in direct opposition to the external field, effectively dragging the total net force inside the material down. A metal conductor cancels external fields by flooding its surface with a highly mobile army of free electrons. A dielectric cannot. Instead, it relies on the microscopic stretching, twisting, and rigid alignment of billions of locked molecules to stubbornly push back. By forcing its own internal geometry into formation, the rigid insulator successfully weakens the electric field from the inside out.